Okay, so let's try this again. Lecture 1C. Uh, this is about science, and I cut this video before, and when it got halfway through, the the video froze, and I just kept on talking. I didn't notice this until I went to edit the video and add some questions. So, take two. Anyways, science, as it said, is a way of knowing. Okay, and in particular, we're talking about knowledge that is subject to validation through demonstration of supporting evidence. And so this qualification, what we mean by scientific knowledge as opposed to non-scientific knowledge, is really one of the key things that I want to get to here, right? You might say, well, isn't all knowledge subject to demonstration through supporting evidence? No, absolutely not, right? I mean, there are plenty of things in which the expectation of demonstration with supporting evidence is not there, right? If I make a statement, it's a bad thing to hurt kittens, right? I know that's true. And I definitely absolutely know it in my bones that it's not a good thing to be hurting animals with no reason or purpose. And so you might say, well, that would be a situation where I've got some knowledge, but there's really no way that you could validate that knowledge with any kind of supporting evidence from the universe, right? I mean, yeah, there are other ways you could basically think about values. You can think about issues that are accepted on faith. The definition of faith is that you don't need to see evidence. That's kind of like what faith is, right? So something where you accept it without requiring any kind of evidence from the world, right? And so, yeah, there are plenty of things that are non-science. And I guess right now what I'm saying here is that in the domain of a science class, you need to restrict our discussion to things that are within the domain of science. And that's basically identified here, right? The book actually talks at greater length about the scientific method. And at least the first section, chapter 1, section 4, you get a goofy example with a flashlight, which I'm not terribly keen on. I'd like to open with a really key example, one that maybe some of you are even familiar with because maybe you've taken a biology class in the past. Now you might even recognize the name Gregor Mendel, it's the genetics guy, right? That's the genetics guy. If for no other reason you remember his name for that, that would be a good start, okay? So what he's demonstrating for us is what we mean by a hypothesis or a model. Okay? I use the term model more or less interchangeable with hypothesis. And basically what I mean by that is some type of testable explanation, okay? And we're explaining something that needs explaining. And that seems kind of redundant, but I want to give you an example to demonstrate this, right? The book talks about, well, the flashlight doesn't work, right? That's a phenomenon that needs explaining. And I guess that does work in a way. I'd like to set it into a more realistic and meaningful context that I think will maybe carry a little bit more impact. And so Mendel is a monk. He's or some type of, in some kind of brotherhood someplace in the Czech Republic. This is in the early 1800s. And he's growing garden peas. And basically he's messing around with his peas. He's able to do these things where he takes the pollen from one plant and crosses it and uses it to pollinate another plant. And so what he does is this thing. I mean, peas are normally self-pollinating. They usually pollinate their own stigmas. They basically pollinate themselves. That's what they habitually do. But what Mendel does is he takes some purple flowered pea plants, pea plants that have purple flowers, and crosses them with white flowered pea plants. Right? It's a novel experiment. Nobody has ever done this before. At least nobody has ever done it before and has recorded the results. And what Mendel found was that when he looked at the offspring of the purple flowered pea plants and the white flowered pea plants, he didn't get like a lavender color flowered pea plant. He got plants that were absolutely purple, just as purple as the purple flowers that we had in one of the parents, right? So this was the children, we call it the F1 of the children of the purple crossed with the white. Okay? And then he allowed these guys to mate amongst themselves. I mean, he could either let them self, or he could do crosses. It didn't matter what he did. But if he had these purple flowered pea plants from the F1, from the offspring, right, crossing with themselves, cross amongst themselves, but what he ended up with are baby plants. You know, he got the seeds, and then he grew the seeds up, and he looked at what colors of flowers that he had. He basically had purple flowers and white flowers. And moreover, he saw that they were in about a 3-to-1 ratio, right? And this is what I mean by some type of phenomenon that needs explaining, right? What he's observing here is, well, on one level, a disappearance of white. The white flower color is completely vanishing, okay, in the F1, in the children of the purple and the white, but then it comes back in the grandchildren, not as common as purple, but basically around 25% of the offspring have the purple flowers. 25% of the offspring have the white flowers. The other 75% have the purple flowers, okay? And so, yeah, this is pretty perplexing, right? If you don't know the explanation, if you don't know the answer ahead of time, this requires some thought. And it might not be entirely evident to you. I mean, if you've never heard this before, it might seem pretty mysterious to you even now. If you've had this explained to you, you might have the explanation in your pocket ready to go. And yeah, I can tell you that what Mendel's model was, his explanation, right, was one involving hereditary particles that eventually, not in Mendel's time, eventually we came to identify them as genes, right? And so I'm going to go ahead and use the term genes. The genes are things that confer purple flowers or white flowers, but every plant carries 2 genes, right? You've got a gene for purple flowers and a gene for white flowers. And the purple flowered pea plants that are always breeding purple are going to have 2 copies of the purple gene. The white flower is going to have 2 copies of the white gene, okay? And when you cross them, the offspring are going to take 1 purple gene and 1 white gene. So these children, the F1 children, are going to have the combination of a purple gene and a white gene. Right? Yeah, but they're purple because the purple gene dominates over the white. We call the white gene the recessive gene, right? But with the purple gene dominating, we don't get a chance to see the white gene at all in the F1, right? But then when we allow these PW plants to cross amongst themselves, we're going to be getting, combinations based on maybe a purple with a purple. Okay, that would be one combination. That would be happening like 25% of the time. You can get a purple and a white. That would be purple, white. You can get a white and a purple. Or you can get a white and a white. And you get WW. And only these plants in the offspring of the F1, called F2, only these plants are white flowered. And all these others, because they're either PP for the purple flowered offspring there, or PW, and in which case the P is completely dominating over the W as it has in the past. And so we'd be getting, on average, an expectation of 3 purple flowers for every 1 white flower. Okay, and this was Gregor Mendel's big idea, right? He said, well, this would be an explanation for how I saw this phenomenon of the white flowers disappearing and then coming back at about in a 25% ratio. That would explain things, right? And so that's that's where he was at probably a very early stage in his investigation, right? Now what Mendel does, he basically takes the next step. Mendel's an absolutely great scientist. He basically says, well, I need to validate this. I need to do more experimentation. So maybe he gets 100 purple flowered plants and crosses them 100 times with 100 white flowered plants, and he gets thousands of plants that he's growing in his enormous garden in the Czech Republic, right? And he basically replicates this. Basically, he does the same thing. He says, out of 10,000 offspring or grandchildren from those parents, we have about maybe 7,500, more or less 7,500 purples and about 2,500 whites. But in other words, I'm able, if I get results like this, that's giving me a whole lot of support, okay, for my hypothesis, right? So basically, he does this experiment. He validates what he initially observed, or actually his explanation. He validates his explanation for what he originally observed, and in so doing, basically, he's making this validation happen over and over again. So another feature of this experiment is that it's highly repeatable, and he goes a few steps further, right? Yeah, he says, well, I'm going to try doing this again with other traits. He crosses yellow seeded pea plants with green seeded pea plants. He crosses smooth seeded pea plants with wrinkle seeded pea plants. He crosses long stemmed pea plants with short stemmed pea plants. And he actually does this for 3 other characters, plus 3 more characters. And in each case, when you get out to the grandchildren, when you get out to the F2, you have about 3-to-1 ratio in the offspring. The green seeds disappear in the F1, but they pop back in the F2 at about 25%. Wrinkle seeds disappear in the F1, and then they reappear in a 3-to-1 ratio in a 25% ratio, 1 out of 4 ratio for in the F2. In the case of long stem and short stem, the long stem disappears in the F1, and then it pops back as 25% of the F2. And basically, he does this over and over and over again. So not only is he validating his explanation, he's showing it to be general, not just for flower color, but for many colors or for many characteristics that he has with pea plants, right? And what I'm trying to tell you here is that with the results that he reported in 1850, he's basically demonstrating exactly what we want to see with good experimental practice, right? He's got a phenomenon that needs explaining. He's got his explanation. He runs a great experiment and demonstrates that his results are repeatable. His explanation is a good explanation for what is going on. It's repeatable. The results, the predicted results are repeatable, and it's also true for many other characteristics. In other words, he's establishing the foundations for why what he's describing here, genetics, is a valid way of explaining heredity. Yeah. Okay. So yeah, I think in a lot of ways, Mendel, we identify him as the father of genetics. He's very much also the father of good experimental practices. So that's our first example. I think it's a really good example, and I think at this point you should be getting a pretty good feel for what we mean by a hypothesis, something that explains a phenomenon that needs explaining. That's kind of like it has to be there in the case of a scientific endeavor. And the testability of the explanation is what makes it subject to demonstration through supporting evidence. In other words, if it's not testable, if there's no way that you can test your hypothesis, then it's questionable about whether that explanation is even scientific to begin with, right? Now, if you go to your textbook, there's another thing that is featured as part of the discussion of experimental science. And so I'm going to share the textbook with you. This is the part where the video froze last time. Okay, and in chapter 1, section 5, it describes something that, yeah, it's another experiment. So this one is fairly straightforward, but it illustrates another feature of experimental design that you should really know about. Okay, and so the general scope here is that we've got two different colors of mice. We've got brown mice, okay, and we've got white mice. Okay, I'm going to draw the white mice over in a different location against blue. The white mouse in the ocean here, so you can see the difference. And actually, there's a white mouse drawn for you right here. And so what we find is that the white mice are abundant in the dunes where the sand is white, whereas the brown mice are abundant in the fields where there's no white sand, but there's a lot of dried grass, dead grass, right? And I think the actual experiment that we're thinking about is pretty straightforward. What we do is we generate fake mice. They're either colored tan or they're colored white. Okay, and we put them out in this habitat and see how many times they get attacked by birds, by hawks. I can see them because the hawks try to grab them and they leave little claw marks in the backs of the fake mice. Right? And so, yeah, you can take your white mice, you can put them out on the white sands, put them out, and put white mice out on the field over here. You can take the brown mice. This is the part that didn't show up and it froze my video. The brown mice, you can put them out on the white sands. Okay, and basically, I don't need to tell you what's going to happen here, right? What he found, what I guess we found was that on the white sands, the brown mice got attacked a lot, where the white fake mice didn't get attacked at all, right? Or very rarely. Okay, on the in the fields, the white fake mice got picked off, and the brown mice got picked off relatively rarely, and so we had a higher ratio of damage to whatever mouse color didn't blend in with the background. Okay, no surprise there, right? There are two things I want to point out here, right? One, this is testable. Okay? In other words, it's also it's possible to refute. It's possible for the experiment that we're setting up to refute the hypothesis. For example, okay, if the white mice and the brown mice got picked off at the same rate, right? 75% mortality for the white fake mice, 75% mortality for the brown fake mice, then that would be a result that would say, no, your hypothesis is wrong, right? Right? That would be like an X mark. Okay? What you have to be able to do, and this is kind of like a higher level of scientific design details, but what you have to do is you have to set up an experiment to basically demonstrate that your model is not wrong. You have to make enough, you have to put enough white mice and brown mice up in the habitat to demonstrate that, to say, well, if my hypothesis were wrong, I would be getting an equal rate of damage to the brown and the white. Okay, but because I'm not getting those results, and my white mice are getting less damage in the white background, the brown mice are getting less damage in the brown background, that gives me the kind of evidence that I need to support the result. Okay, so that's part of it. The second thing is that we need to have controls, right? It wouldn't be enough, for example, to put out a bunch of brown mice, I know they look like little poops, in the white habitat and to demonstrate, oh yeah, they get damaged all the time. It wouldn't work for you just to put the white mice in the, put a bunch of white mice in this habitat with background, with the brown background to show that they got picked off a lot, because that wouldn't be demonstrating anything, right? We need to have something to compare it with. And in this case, the controls allow us to demonstrate that it's not simply the hawks picking off the clay because that's what they do. They're actually picking off the white mice at a higher rate relative to the ones that are not camouflaged, relative to the ones that are camouflaged. The non-camouflaged ones are getting damaged at a higher rate compared to the camouflaged ones. Okay, I said it correctly that time. Okay, and so yeah, having appropriate controls and having appropriate sample size, these are all things that are kind of good features to have in experimental design. Okay, I go back to the whiteboard and expand this a little bit and see what we've talked about. Yeah, we've talked about example 1 of good experimental practice, experiment 2, the one from the textbook. I like to anchor things in the textbook every once in a while, especially when I go off in my own direction, right? And now I want to give you one more example, right? This is also going to be from the textbook. This is going to be based on the red panda question, right? Remember that from the text? Red pandas, more closely related to raccoons or giant pandas, panda bears. Right? And so let me get that textbook out again. So back to my share text. Be looking at this chapter 1, section 6. Who are the red panda's closest relatives? Now you might notice here that we're not really setting up an experiment that is subject to the normal kind of manipulation. Here's the control group, here's the experimental group. The thing that's important here is that we're still setting up a question, a hypothesis that can be validated using observation from the natural universe. Okay? We're interrogating nature to provide us with the information that we need to establish an answer, right? And so the question at hand is, should we say red pandas, they're basically raccoons, kind of look like raccoons. They look a whole lot more like raccoons than they do like the giant pandas. Or do we classify them with the giant pandas because after all, they're both called pandas, right? And they both have a kind of an interesting characteristic. They've got a little weird thing on the wrist that allows them to function, allows it to function like a little thumb, right? And so the question of, well, should they be in the should they be with raccoons? This would be in the family, the Procyanidee. Okay. Or do we have them together with the giant pandas, which are in the Ursidae? This is the bear family. Okay. You got the raccoon family and the bear family. This is a taxonomic name. Usually when you come across a name like this, AE at the end, you say E, right? So Ursidae, not Ursidae, right? And the Procyanidee is the raccoon family, right? And where do we put them? Well, is it just a subjective thing? Do we just say, well, I think they kind of look like pandas, like raccoons? No, I think they look like pandas. That would be entirely subjective. I mean, everybody would be entitled to their own opinion. What makes it scientific is that we actually have some evidentiary support for one hypothesis or the other, right? And it turns out that the red pandas are more closely related to the raccoons. They share a relationship together with skunks, which are in the Mephistidae, and the raccoons, two C's, I think. Raccoons, Procyanidea, and it turns out that we put the red panda into its own family, okay, which is the Iluridae, right? And these guys are more closely related to each other than they are to the bear family, which includes the giant panda and the brown bear, the grizzly bear, and the black bear, and the polar bear, and the and so we've got all the bears over here, and the bears are more closely related amongst themselves, whereas the skunks, the raccoons, and the red pandas are more closely related to each other, right? How do we make this determination? You know, this is basically a scientific statement, a scientific model, and it's based on the evidence that's provided to us by two things. One is the morphology, right, which is the physical traits. Right? There are similarities, like maybe the fact that you've got a nice big bushy tail with stripes. That would be an example of a morphological trait that would be shared between the red panda and the raccoon, which would not be shared with the giant panda. You could list all the traits, like the cute little nose of the raccoon and the red panda, whereas you got this big old schnoz on the giant panda. One thing that would link the giant panda with the red panda is that little thumb-like appendage. And so if you total up the number of similarities, you might see a greater number of similarities over here compared to over here, right? The other thing is we use molecular traits, molecular information, in the DNA, the A's, the C's, the T's, and the G's. When you look at comparable genes, is a sequence of A's, C's, T's, and G's more similar between the red panda and the raccoon, or is it more similar between the red panda and the giant panda? And again, it seems like this linkage over here is stronger than the one that we have between the red panda and the giant panda. Okay. So I guess my point here is that we don't always have an opportunity to conduct an experiment of per se, although it's kind of like a thought experiment to say, well, what would you expect? What would be our expectation if the red panda were more closely related to the raccoon? What would be my expectation if the red panda were more closely related to the giant panda, right? And in that sense, we're basically fulfilling predictions or expectations, matching up with what we might be hypothesizing in our model. Let me go back to, let me erase everything that's here. So I've got, nope, I don't want to do that. Let me just not erase everything that's here. Let me just erase, we have close to the bottom. It's going to do that, okay? Now, this is an important thing for us because I think one of the misconceptions that people have, I mean, some scientists actually say the wrong thing here, right? Yeah, I think this misconception is a pretty serious one, because it's serious to me because it basically tells me that a person is not really understanding the process of science, right? So if you think that a scientist is in the business of proving facts, right? Well, that's wrong. Okay, the answer to that is no, absolutely not. Okay, that's not what a scientist does. scientist doesn't prove things at all, right? Facts in particular don't need to be proven because they are facts, right? Kind of like what a fact is, right? You don't need to prove something if it's already factual, right? So I guess maybe I should generalize this. Does a scientist prove theories, hypotheses? No, we don't have any proof, because a proof basically means not refutable, right? If something is proven, then it's a fact. At that point, it's a fact, and you can't refute it. Okay? The whole point of science is that we're dealing with testable explanations, things that could theoretically be falsified, things that could be refuted given the right kinds of results or actually the wrong kinds of results, right? Because, so you know what I mean, right? So proof is not really in the domain of what scientists typically do. I mean, proofs are things that mathematicians do, because in the world of mathematics, things, if you have A and B, then you could prove that C must occur. I mean, proofs are definitely things that people do in some situations, but because of what I've just told you about the nature of science and the nature of the kinds of things that science asks about the natural universe and the way that we're interrogating the natural universe for support, in contrast with other results that might give us refutation, that by its nature is telling us that we never really prove anything in science. The scientific proof is really never really proof. I mean, it's not something that really happens, okay? And so, again, if somebody says that it's scientifically proven that, right, that's like a big red flag. That tells you that this person really does not understand the process of science, okay? What does science do if not prove, right? I mean, science, okay, it can offer support for a model. Experimentation may offer support, or it might offer a refutation, right? And we tend to pay attention to the scientific models that actually have support, because we don't really need to teach scientific models that completely lack any support whatsoever, okay? So yeah, science, what it does, it offers support using observations from the natural universe, but we never completely prove them, and we can also never disprove them, right? We could demonstrate that they're not supported, but that also leaves open the possibility that the experiment was not done correctly. There might have been something wrong with the experiment that would cause us to consider that maybe refutation that we're looking at is not as as uncontroversial as you might initially imagine. Okay, that's it for this lecture. I'll see you next time.